Hello, everyone. A very warm welcome to all of you. Today, we are going to talk about something that is fantastic, all inspiring, and exciting realm of wireless communication systems that has disrupted the entire IoT universe into so many profound ways, and that is LoRaWAN. I'm pretty sure that you will enjoy this webinar as much as we enjoyed making it and introducing it to you. A bit about myself, I am Manvendra Singh, being with SenRa for the past 10 months, and in the LoRaWAN universe for around 2.5 years since my bachelor's in electronics and communication. I have to say, and I wanted to add it, that every day at SenRa is filled with thrill and excitement because each day is a golden opportunity for all of us to dive deeper into the ins and outs of this amazing wireless technology that is LoRaWAN. So I'm very eager to share with you everything gradually with this series of webinars. So what's today's agenda? The very first thing that I kept on the slide is to help you differentiate between these two very interchangeably used terms, that is LoRa and LoRaWAN. And we'll get a slight flavor of what a typical LoRaWAN architecture looks like. Very basic. Then we'll take a leapfrog and try to understand the three main characteristics that LoRa has and why it has those. Right? That is long range, low power, and low data rate. Afterwards, we'll try to see which are the different issues that are addressed by LoRaWAN and why it all is important. And finally, we will have a Q&A session about which I'm really excited about. Guys, ask as many questions as you can in the Q&A box that you'll see after the 45 minutes of when I speak. Cool. So the difference, the very first thing, two very interchangeably used term LoRa and LoRaWAN. What are they and how they are different? The difference can be very subtly observed when we see the OSI model. For all wired or wireless networks, we have different layers. Each layer has its own protocol, all right? Now, LoRa, if you would see, lies in the bottommost layer of the OSI model, all right? It's the most bottommost layer that is called the physical layer. However, LoRaWAN lies in the data link layer, particularly since data link layer divided into DLC and MAC, LoRaWAN lies in the MAC layer of the OSI stack. What does a physical layer do? It's very important to know that any information that has to be transmitted over there wirelessly has to be first converted into electromagnetic signals, because air doesn't understand your information. All it does understand, though, is the electromagnetic signal. So it's the responsibility of the PHY layer, the layer at the bottommost layer of the OSI model, to convert your information into something that could travel over there, that is the electromagnetic signal. However, the duty of a DLL is about essentially framing, flow control, error control. What are they will gradually look. So, but you have to know that there are two different things lying in different positions of the OSI model. And very importantly, that LoRa standard is proprietary. It's a closed source, it's a patented technology. However, LoRaWAN is public and it is taken care of by LoRa Alliance. Cool. Now that we know the two differences, let's get the flavor of how a typical network architecture looks like. The first thing we have in the network, which is present in bulk, is the end devices. End devices are everywhere in the network. They essentially have a sensor in a typical use case with a microcontroller and radio. These devices would send data over the air to the LoRaWAN gateways, right? So these devices would capture some sensor information, process it, and then wirelessly transmit it over the air using the radio modules. And we capture those electromagnetic signals on the LoRaWAN gateways. All that information is then routed to the network server, a centralized network server to which all the possible gateways that we have in India are going to a centralized network server that is called as a network server. From there, things go to the dedicated application servers. Good. Now that we know the basic architecture and understanding that there are two different things, it's the right time that I wanted to talk to you about today's topic, since you know about it. Now I've compartmentalized this webinar into two parts. The first section is solely dedicated for LoRa, and the other section is solely dedicated for LoRaWAN. Okay? Now, since we know that there are two different things, let's see what we are going to talk about in LoRa. In LoRa, we will not give you cliche definitions. I will not share with you technical jargons. Rather, I will focus my understanding just so that you understand why LoRa essentially have these three major characteristics that it is famous for. And while I do so, there will be a bunch of technical jargons that you will take away as your vocabulary, right? While we take a transit from LoRa to LoRaWAN, I'll try to create a bridge a bridge which help you understand that why at all any MAC layer is important that is riding on top of a PHY layer in any communication technology is important. And when we understand that, then when we get convinced that there has to be something that has to be riding on top of LoRa, that is LoRaWAN, we'll try to see what are the different issues that LoRaWAN addresses. That is the addressing mechanism, security, and device classes, and so on. Note that that would be a very 101 overview. We'll not get deeper into the facts, but we'll try to get a superficial understanding of all the things. All right, let's begin. LoRa. In order to understand LoRa, I would ask you all to first close your eyes and remember your best friend. And imagine as if he's standing on the roof of his house and he's trying to say something. Note that anything, as I said, any information that has to be wirelessly transmitted over the air first has to be converted into electromagnetic signals. So there's a modulation from information symbols to electromagnetic waves. And our human body also does that modulation. And hence, what we transmit over the air are electromagnetic signals and that are essentially sound signals. These sound signals, let's say they are traveling over the air and we are standing a given distance away and we are trying to hear what our friend has to say. And we're easily able to comprehend what our friend is trying to say to us, right? However, in some case, we realize that a person who is a bit far away from the source, from our friend, a D1 plus D2 distance away, is also trying to comprehend what's going on in the network. But he is unable to do so. It's very intuitive to understand that since we are standing just a D1 distance away, the intensity of the power that we are receiving is something that we can make out of, we can make sense out of. But the person that is standing D1 plus D2 distance away, the intensity of the power that is reaching him is way too less than what our human ears are sensitive to, right? Our human ears are sensitive to signals that are above a certain threshold. If the signals that are reaching us below that threshold, we cannot make sense out of it, all right? So now that you understood this analogy, believe me, 25% of what we are gonna cover today is already done. Because now I'll map this analogy to the wireless technical jargons. The first one is, as you'll see, just give me a moment. Yeah. So the very first one is the transmission power. So as I said, our friend is trying to basically accumulate some power, and then he's trying to radiate those electromagnetic signals. In this case, there are sound signals. So he's accumulating a transmission power and irradiating that into the universe, right? So that is called as a transmission power. Also, we understood that when waves travel a medium, they tend to have an attenuation associated with them. So that path essentially where they travel have an attenuation, right? So that path has a path loss associated with them. That is a function of distance. More is the distance, more is the path loss. Note that path loss is also a very function of other things, but we have kept the discussion very simple. So path loss is a function of distance. The third thing that we understood is that the received power, the power that we are receiving. We understand intuitively that that power is lesser than what was transmitted. To quantify that, it's basically a subtraction between the transmission power and the path loss. So that's received power, the power that we receive. It's lesser than what was transmitted. It's the difference between TXP and the path loss. Also, we understood that the last friend that we have at D1 plus D2 distance away, was not able to comprehend what's going on. Because the signals that were reaching there were lesser than the threshold, the sensitivity level of our ears, right? So that essentially happens in general in wireless communication. We call it as we call that threshold below which we cannot understand the things as the receiver sensitivity. So believe me, you have already covered 25% of what we are going to talk about, because if you know what's TXP, path loss, received power, and receiver sensitivity, you're well equipped to understand why LoRa is a long-range communication technology. But before we do that, let's score full marks. Let's also try to understand what's the unit of power that we are dealing with. Just the 4 terms that we just discussed. Let's assume that when we are talking about power, the first thing that pops up in our head is watts, right? So let's just assume that our friend is accumulating 1 watt of power and transmitting it over the air. And due to path loss, the received power at certain distance D1, let's say 20, 30 meters, it's 0.6 watts. And the signals up to which our ears are sensitive to, let's say it could be 0.2 watts. So receiver sensitivity is 0.2 watts. Believe me, guys, had it been that simple, wireless communication would not have suffered a lot of problems. Because if I were to represent all of that in an actual wireless scenario, if 1 watt is transmitted over the air, due to path loss of only 20, 30 meters, this is the amount of power that you received at 20, 30 meters. And if I were to represent in watts the receiver sensitivity, this is how it looks like. So we have already gone to 20, 10, 12 decimal places. And we hate decimals because they make our calculations really horrible. So we had to come up with something that makes our calculations easier. And that was dBm. If I represent 1 watt into dBm, this is how it looks like, all right? And 0.000001 watt, this is how it looks like. And now I can see that I have represented a very big number into a very small number that is easy for all our calculations. Cool. We understood what's transmission power, path loss, received power, and receiver sensitivity. We also understand that what is the unit of power that we're talking about. Now we're well equipped to understand why LoRa is a long range communication technology. And believe me, guys, I'm not using any more terms that I just spoke about. This is all we're going to use. Assume that this time our friend is not talking, rather he is using a Bluetooth module. And he is accumulating 1 watt of power. And as we know, 1 watt is 30 dBm in dBm units. And he's using that to transmit those signals. When those signals would travel, let's say a distance of 20 meters, there is a path loss of 100 dB associated with them. Now, since we know that received power is the subtraction between the transmission power and the path loss, the received power at distance of 20 meters is minus 70 dBm. Now, guess what? The receiver sensitivity of Bluetooth module is around minus 70, 80 dBm. And hence, even though the signals are traveling far across in the universe, the problem is at those points, the received power is lesser than the threshold. This is lesser than the receiver sensitivity, and hence they cannot be comprehended at those points. So that's why the range of the Bluetooth is only, let's say, 20, 30 meters long. Let's cementify our concept by taking an example of Wi-Fi, right? So let's say if I have a Wi-Fi signal, if I transmit it using 30 dBm from the source, it travels a little larger distance of, let's say, 30 meters, and it incurs a path loss while it travels through that medium of 110 dB. Note that I'm increasing my path loss as I increase my distance, because we know now that it's a function of distance, just to simplify our calculations. At 30 meters of distance, at this time, the received power is minus 80 dBm. And guess what, guys? Actually, the Wi-Fi signals have somewhere around minus 80, 90 dBm of receiver sensitivity. And since signals would travel far away in the universe when they're transmitted from the source, but at those points, it is already lesser than the receiver's sensitivity, and hence they cannot be comprehended at those points. That's why receiver sensitivity limits the range of any wireless communication technology. But then what's special with LoRa? Why it got so famous, right? So when I'm using LoRa and transmitting those signals with 30 dBm of transmitted power from the source, it will travel a massive distance of kilometers, right? It will incur a path loss of 170 dBs, and the received power would become 30 minus 170, that is minus 140 dBm. But the point to note here is that the receiver sensitivity of a LoRa signal is around this point. It's around minus 140 to minus 147 dB. And hence, even at those positions, we can hear LoRa signals. So what we understood from here is that LoRa, since it has an exceptionally low receiver sensitivity, it is called as a long range communication technology. All right. Now that we understood long range, because it has an impressively low receiver sensitivity, we are also well equipped to understand why LoRa is low power. For that, we'll take just 4 things that we learned, all right? Transmission power, path loss, received power, and receiver sensitivity. But this time, rather than using 30 dBm from the transmitted source, I'm using 10 dBm. And since I've decreased my transmission power to 10 dBm from 30 dBm, the received power at this time at 20 meters would become only minus 90 dBm. We know that, as we assume that the Bluetooth signals have a receiver sensitivity of minus 70 dBm, this time the received power at 20 meters has dropped down well below minus 70 dBm. Hence, Bluetooth has a black spot over there. We cannot hear a Bluetooth signal when it's transmitting at 10 dBm and 20 meters, because its receiver power is lesser than the receiver sensitivity. And hence, for any communication technology, if we reduce the transmit power, the received power would become lesser, and hence the range shrinks. And that would happen for Wi-Fi as well. Rather than using 30 dBm, I'm using 10 dBm this time. At 30 meters of distance, the path loss is 110 dB. The received power this time would become minus 100 dBm, which is lesser than minus 80 dBm, which is the receiver sensitivity of Wi-Fi. There's a black spot for Wi-Fi again. And hence, for any technology, the range shrinks when we reduce the transmit power. And that's true for LoRa as well, right? This time, which was earlier minus 140 dBm, it's minus 160 dBm because we have reduced the transmit power. We also have a black spot for LoRa. But the point is that we can still cover the range that we want. We can compromise with a slightly lesser range if we reduce the transmit power. And that's the beauty of LoRa. At low transmit power as well, we are getting an impressively long range, all right? But the question is, if we were having a very impressively large range, why would we decrease our transmit power and compromise with the range? Why we at all went to this point? Answer to that lies in the end devices. End devices have batteries associated with them. And every time when we do a LoRa transmission, let's say, the radio module sucks in current from the battery to do that transmission. So assume that we are transmitting a LoRa signal and we are using 30 dBm of transmit power and 10 dBm of transmit power. At 30 dBm of transmit power, the current that we consume from the battery is 125 milliamps. However, in case of 10 dBm, the current reduces down to 30 milliamps. Now, what if we use 10 transmissions a day? The difference is big, right? So we are always consuming more current when I'm using a high transmit power. What all that is trying to say to us is that with high transmission power, yes, we can reach a very long range. But since you suck in more current from the battery, our batteries drain in no time. And who wants that? That's why we wanted something that is not just long range, but with a low power that gives us the long range capability. And hence LoRa fits in real well at this point because it's both low power and long range communication technology. Cool. We have already understood two major concepts of LoRa, that it is long range and low power. Now we are easily and very well equipped to also understand the trade-off that we did. Right? We bought long range and low power at some cost, and that was a low data rate. That's the trade-off that we did. But whether or not this trade-off was clever or not, that's up to us to decide. And we'll investigate that. And we would first have to investigate what is the data that we are talking about in any wireless sensor network. Is it a video that we want to transmit over the air, which is in the order of gigabits or megabits per second? No, right? We don't even want our devices to sing a song, right, over there. We don't want audio signal to be transmitted, which is in the order of hundreds of megabits. All we have to do, that we have to wirelessly transmit from the end devices, is the sensor information. And what's the typical size of a sensor information in wireless sensor network? We'll try to convince you with an example, because it's very less. Let's take an example, a very common IoT use case of a smart bin. In order the dustbin to become smart, it has to capture bin fill. What is the bin fill level of the dustbin? How much fill the dustbin is? And map that into a range of 0 to 255. From our high school math, we know that a number within the range of 256 could be represented using only 8 bits. So you see, videos are in gigabits, megabits. Audios are in all the order of megabits. The sensor information can be captured with just 8 bits. But let's be realistic and let's make our dustbin even smarter. Let's assume that it has another sensor associated with it. And that sensor is a temperature sensor. And it's capturing the ambient environment temperature. And that could be in the order of minus 50 to 50 degrees Celsius, as we know. Again, since this is a number within the range of 256, it could still be represented using 8 bits. Even if I add some more overheads that LoRaWAN adds, the typical size is around 20 to 50 bytes. So it's not much. We're not talking about gigabits or megabits video or audio transmission. It's just mere 20 to 50 bytes. So the trade-off that we did, the something that we bought that is long range and low power at the cost of low data rate, was a very clever trade-off. Because we knew that the data itself isn't that big. So why not reduce our data rate and get what we want? So that's why I will always say that it's a very clever trade-off that the LoRa inventors did. Now is the right time that we also talk about what are the different data rate options that we have in LoRa. So on the x-axis, you see there are different data rate options, data rate 5, 4, 3, 2, 1, 0. At data rate 5, the bits per second with which we can transmit over the air is around 5,470 bits per second. Right? So it is in the order of kilobits per second, basically 5 kilobits per second. And I've taken as a reference a 10 bytes of payload. At 5,470 bits per second, a 10 bytes of payload will only take 34 milliseconds to transmit over there. Cool. But we see that there are other options of data rate also available. At data rate 4, the bits per second that LoRa radio allows us to transmit is 3,125 bits per second. And to transmit a payload of 10 bytes, it would take now not 34 milliseconds, but a slightly more time, that is 68 milliseconds. As we decrease down the data rate, now we know the curve, that is, this is how it looks like. As we decrease the data rate, we are decreasing the bits per second, and hence the amount of time it takes to do a transmission of 10 bytes payload essentially increases. All right. The summary is lower the data rate, higher is the transmission time that we take to do a payload transmission of same bytes. But the problem is with the lower data rate, we are decreasing the bits per second. We are taking more time to do the same transmission. The question is, why at all do we want to go for a low data rate option when we already have a data rate option that is data rate 5, which is giving us 5,470 bits per second? Why would we at all want to reduce our data rate? Answer to that lies in the understanding that we already have. This time on the x-axis, I again have data rate. Let's assume that the transmission is done using data rate 5. We now know that a 10 bytes of payload would take only 34 milliseconds over there. At data rate 5, the receiver sensitivity that data rate 5 signal provides us is minus 124. That means when the signals would travel, after minus 124 dBm received power, they won't be heard of. But in case of data rate 4, let's see what happens. We know that we are decreasing our data rate. We are taking more time to transmit the payload, but the receiver sensitivity seems to be getting improved. From minus 124, we have reached minus 127. That simply means that our signals can still be heard of at a longer range. So as we decrease our data rate, we know that we are taking more time to transmit the same bytes of payload, but we are getting a longer range essentially because we are having an impressively low receiver sensitivity at a low data rate. And hence, a low data rate signal could travel a longer distance because it has an impressively high, or impressively low, essentially, the receiver sensitivity. Cool, right? I'm sure the summary is the lower the data rate, slower the transmission, yes, but longer the range we get. And I'm pretty sure the next time that you'll see this table that you would always see when you're working on the LoRa universe, this is a typical table that you'll see in the data sheets. That data rate, there are 6 data rate available. This is the bits per second. The time on air is simply the time that it takes to do a transmission using data rate 5. I have taken 10 bytes of payload. You take 20 bytes. This is simple unitary method. Also, we know that different data rates have different receiver sensitivity, and hence they provide different ranges. Cool. I would summarize this for you just so that you remember it forever. We understood that we took long range, low power. We bought these two things and we traded off with low data rate. For a long range, a communication technology should have an impressively low receiver sensitivity, and that LoRa has. It has to be also low power because we are not having infinite amount of batteries. So we also have to take care of the battery life. So the communication technology should be both low power and long range. And we understood that we traded off with something which was a very clever trade-off, because we understood now that the data isn't that big. We didn't require a very large data rate. So we gave it and we took what we want, that is long range and low power. I would love to have this questionnaire, but let me answer the questions that I asked you. So if there's a real network in the environment, as we go away from the gateway, as we go away from the receiver, what essentially decreases? Since the path loss increases with distance, the received power basically decreases. So the nodes that are far will have a lesser RSSI. The received power would be lesser at the gateways. And hence, they have to use a high transmit power to mitigate that path loss. Also, we need to use signals that have impressively low receiver sensitivity. And we know that data rate 0, data rate 1, these are the ones that have a very low receiver sensitivity. And hence, the ones that are far should also use a low data rate. So that's the summary. We now know that we do trade-off between long range, low power, and low data rate. We know why LoRa is long range. We know why it is low power. We understood the trade-off that we do. And this is how we can map our understanding to a real network. Cool. The next thing, it's even amazing than what we just discussed. That was LoRaWAN. But the first thing that I wanted to do is to try to convince you that there has to be something that is riding on top of LoRa, because we are already getting low power and long range. Why at all do we require something riding on top of it? That is LoRaWAN. So we are bridging the gap. We are now trying to understand what's the importance of LoRaWAN. For that, assume that we have a gateway. and gateway has this coverage. And within that coverage, there is an end device. And that end device is trying to talk to the gateway. While it does so, it will irradiate its signal with a transmit power all across in all possible directions. Right? But the question that we should ask is that is it the only end device in the network? No, right? We have multiple end devices and that of multiple use cases. So all of them are using the same shared medium. All of them are using the same wireless medium to connect with the gateway. So in practical life as well, if two entities are sharing the same shared resource, if we don't have a standardized protocol that both of the entities should abide by, there would be a chaos. So we needed something that would help end devices access this medium, the shared medium, in a control sense. And hence LoRaWAN is crucial because it is a medium access control protocol. Cool. But we are still not convinced. We are not trying to assess what are the different issues that it addresses. So the first one is addressing issues, right? So if we have a gateway and a network established in this sense, if the end devices are the ones that are trying to initiate the conversation, that conversation is called as the uplink. However, if the application server or network server wanted to transmit the signals, they would relay those signals via gateways, and this is called downlink. So we'll focus our understanding on just uplink for a moment. So whenever end device would initiate the conversation, that is known as uplink. So what does uplink frame contain? An uplink frame essentially contains preamble, PHY header, PHY payload, and CRC. What do they mean? We'll see in the webinar. We'll save this discussion for later, but all we need to know is that the PHY payload has the information that we want to transmit over there. It has essentially all the sensor information that we wanted to transmit. But the problem is, where is the address? It has all the sensor information, but we don't have any address. But we need something called address because we have a lot of devices. So there has to be a network address associated with those devices. And somebody has to take care of that. But is it the duty of the physical layer? No. All we know that physical layer is meant to convert information symbols into electromagnetic waves. So it's not the duty of the PHY to take care of that. So somebody has to address the addressing issue, and that's where LoRaWAN comes into the picture. It gives network address to all the end devices just so that gateway tends to understand who is the one who's talking to me, who is the one that is sending the payload. Cool. But let's get even more convinced. Let's try to see what are the other important issues that LoRaWAN addresses. And that would for sure convince you that there has to be something that has to ride on top of LoRa for a seamless and efficient network. And that is the issue of security. If we have an end device and gateway in that sense, and the end devices are initiating the conversation, and this is the packet that is receiving by the gateway. But what if there is another gateway in the picture who's trying to receive what's going on in the network? And this is the gateway to which we don't want those packets to be sent to. Right? But since we are using RF medium, it would reach there. And if I would want to break both the packets, the packet of the packet that is going to the intended gateway and the packet that is going to the unintended gateway, they necessarily look the same. They contain the same information. But we don't want the unintended gateway to understand what's going on. And for that, we require encryption. And who would do that encryption? It's not the duty of the PHY to do that encryption, but somebody has to take care of encryption mechanism to embrace security. And hence, LoRaWANs come to the picture. It would secure your packets in such a way that only the intended network server are able to understand what's going on, not everybody. The last issue that is really important that has to be present in almost all IoT use cases that you could think of, and that is the bidirectional communication. What's that? If we have a gateway and network in that sense, most of the traffic belongs to the uplink. Almost end devices are the ones that are initiating the conversation. So network is filled with uplinks. All these uplinks are routed to the network server and then to the application server. But what if we want to instruct something to the end device? This time we don't want end device to send packets to us. Rather, we want end device to listen what we are going to tell to it, right? And that is really possible because if the network server would want to initiate a conversation, it has to send something to the end device via downlink. This could be an instruction. For example, for a smart bin, you would want to say that, hey, don't transmit payload when you are above 200, but transmit it when you are above 100. So we want to change something. We want to instruct the end device, right? So we need some instruction mechanism, and those instructions can be relayed over to the end devices via downlinks. So all that we said, what all of that is trying to say to us, we need a sophisticated protocol. right? We need something that both the end device and the gateway should abide by. All right. So that would happen in real life as well. If we have two entities that are trying to have a bidirectional communication, if we don't have a sophisticated protocol to both of them, everything would be a chaos. So that is taken care of by LoRaWAN. LoRaWAN has class A, class B, and class C end devices. What are they? What do they do? Let's just see that. So if I have LoRaWAN device classes into the picture, class A, class B, and class C, we'll see the time domain waveforms. Every time when a class A end device does an uplink transmission of time on air period, it will wait for some time and then open its receiving one window. In this receiving one window, essentially, it will try to capture what's going on. It's try to capture the downlinks. After that, it will wait and again open a receiving window in which we'll try to see if it has missed the downlink. So the gateway essentially have those two periods, RX1 and RX2 window. In that period, the device would capture what's going on. It will be in a reception mode. But after these two windows, it will go to a sleep mode. It won't listen to anything, nor it would transmit. It will just sleep. And only after a long period of time, that could be a 1 day, 2 hours, 5 hours, it will open its transmission slot and again would open its to receiving slot. But in case of a class B end device, when we are doing an uplink transmission of time on air period, it would again open the receiving window of RX1 and receiving window of RX2, and then it could go to sleep. But the change here is that it has to again wake up after some time and try to listen to what's going on in the network and see if there is any downlink coming to it. If not, it would again go to sleep. And again, after a long period of time, that could be say minutes or hours, it would have to again wake up and try to see and try to capture what's going on in the network. So over in the class A end device, we have an ample amount of time to sleep, but a class B end device doesn't have that much of privilege. It has to again and again wake up in slots to see if there's a downlink communication going on in the network. And that's how a class B end device would work. Class C end device, however, follows the same maneuver. It will do the uplink transmission, it will wait for some time, then it will recept in RX1 window, then it will again recept in RX2 window, but this time it doesn't have the privilege to sleep forever. It has to be in the position of a reception after its receiving two window. There's no time to sleep. And hence, this is how time waveform of a class C end device looks like. What all this is trying to say to us is that if we see which of class A, class B, or class C end device works best for a longest battery life, then we realize that it is class A. Because we have most of the time sleeping. We don't have to wake up again and again, or we don't have to wake up for the whole period of time. We have an ample amount of time to sleep. If all the end devices of class A, B, and C are using a battery, class A would work for the most of the time. But what's the trade-off? We always see there is a trade-off. The trade-off is that if you want to communicate, if you want to instruct a class C end device, we can do it right away because it is always listening. Class B end device would listen to you in slots, but class A end device would only listen to you after it does the uplink transmission. So that's why latency is least in case of class C end device, and the latency is most in case of class A end device when we are doing a downlink transmission. So that's the whole thing. That's LoRa and LoRaWAN. We saw where are the different issues that LoRaWAN addresses. And now is the time that we do a conclusion and we try to talk to you about the future work that we are going to do. So we first understood what's the difference, what's the architecture. Then we talked about why LoRa is long range, low power, and low data rate. We moved on to understand and we tried to see what are the different issues that are addressed by LoRaWAN. The future work that I'm really excited about is LoRaWAN 201. I had to restrict all of my explanation because it was a 101 webinar, but there are ample amount of things because we have to deal with spreading factor, whitening, interleaving, whatnot. Everything in the LoRa is left aside. In LoRaWAN, we haven't yet understood how these different issues are actually addressed. So that's reserved for 201, right? So buckle up, guys. We are very interested to show you LoRaWAN 201 whenever, and it will be a very detailed session. Now is the time that we do a Q&A session. I can see a lot of questions already popping up. Thank you all very much. I'll take your questions one by one. And you can always reach to us at info@senraco.com or support@senraco.com, and we'll be ready to answer all the questions. Cool. Let's see the questions now. I'll try to see the questions. Just go to Zoom. Okay. Cool. So we have questions, a couple of questions here. The first one is, can we use directional antennas at gateways to improve RF performance? Okay, just hold on a second. I'll just do one quick thing, that I'll share my screen with you all, just so that you know that where you can reach us at. Okay, perfect. I'll try to jump on to the questions. See, perfect. So there it be. So the first question is that, can we use directional antennas at gateways to improve RF performance? Yeah. So that's something that we also use. It could happen that in some regions we don't have that much amount of coverage. So what we do is that we fix our antenna beam width to certain direction, and in that direction, the receiving gain at those direction essentially gets higher. So we have a higher link budget in that case, and hence we can reach a longer range up to 1.5 to 2 times of what we can use in omnidirectional antenna. We could go 1.5 to 2 times in directional antenna in that particular region. So yeah, directional antenna would have shrink bandwidth, beam width, and that would help end devices to communicate at a longer range. So yeah, we use directional antennas at the gateways. Okay, let's see. How is the best way to configure the spreading factor SF? Okay, so we didn't talk about spreading factor because, but that's related to data rate. At a fixed data rate, spreading factor and data rate almost mean the same. But the question is that best way to configure the spreading factor, that if you're really far from the gateways, right? The first thing that you could do is that you can enable the ADR, it's adaptive data rate scheme, right? So what does that? What it does is that it will take a couple of SNR values at the receiver and see how far basically you are in the network. It will understand what's the link budget that you're going through, and it will automatically switch itself to the best spreading factor at your place. So LoRaWAN helps in enabling the ADR mechanism that you could always do. It's not that always the highest spreading factor is the best, because higher spreading factor means more time on air, and more time on air simply means that we are taking more energy for the same transmission. So it's not always good to have a higher spreading factor. What's best for your end device could be easily decided by the ADR, because ADR will take care of the fact that where basically you are in the network, what's the link budget that you have with the SNR values at the receiver at the gateway, and then it will try to give you the best SF value. So yeah, that's the best way to configure spreading factor. Cool. Let me just see. Yeah, is there a frequency band for LoRaWAN? Yeah, so basically, if you're using LoRaWAN in India, that is defined in the regional parameters, you will be using the Indian ISM band that runs from 865 to 867 megahertz, right? So there are 8 channels in between. You could use any of those channels. 3 channels are mandatory, but the frequency band is limited to 865 to 867 in India, and that essentially differs from region to region. So wherever you are, you would want to check LoRa Alliance page, wherein you'll find regional specs. And if you are in India, I would say it's 865 to 867. That's where our ISM band lies. For other countries, it's different. Okay, let me just see. So I understand. Okay, I'll just repeat the question and let me see if I can understand that. So I can understand that LoRa has message length restricted to 50 bytes. My question is, does this mean I can fill all the 50 bytes with the data I need to transmit, or this 50 bytes into device ID, bytes occupied encryption, and error checking and other padding bytes? If so, that's maximum length that I get finally after eliminating the padding bytes for error checking and bytes is used for encryption. My point of this question is location data typically takes over 16 bytes. Yes, location data takes in that much. Yeah, so I understand your question particularly. This could be perhaps a solution where you're saying that you want to do latitude and longitude transmission. We do that too. And we use typically, 16 to 24 bytes, because we are also adding some other temperature sensor and other sensor values, and we do that transmission. Your answer, I would like to give that detailed answer, because your question is like, if the forward error correction bits and everything, because we didn't talk about code rates here, right? When we add code rate, that means that we are adding parity bits. And if that is added, that means that the total bits that we want to send is increased. But that's essentially because that you want to better, for error correction. I would like to answer that question in detailed sense. Mathematically, I'll try to explain you. But note that 50 bytes is the entire thing. I mean, the device ID and whatever you want to add, it's the LoRaWAN packet size, not just your information. So it's the complete thing. But what you can do if your data size becomes larger than 51 or 50 bytes, you can always defragment and fragment, right? So that's the thing that you could do if your payload size is increasing more than that. But if you want to check with that, I will give you a perfect answer via an email. But if you want to really check, you could go to LoRaWAN's website and see that in India, we have the highest splitting factor. You could use 51 bytes. That is basically more than what we could use in US or other countries. So we have a large buffer. We could use 50 bytes, 51 bytes at lowest data rate. That is data rate 0 SF12 and 125 bandwidth. I would love to answer that question in detail for sure. Okay, so one question I see that since LoRaWAN is proprietary protocol of Semtech, can it be? So as I mentioned in the initial phase, that LoRa is proprietary, LoRaWAN is public, and it's taken care of by LoRa Alliance. So I have to again mention that if that's not clear, that LoRa is the one that is proprietary and it's patented by Semtech, but LoRaWAN is taken care of by LoRa Alliance. It's public, and you could also contribute to that. Another question is, does LoRaWAN protocol provide acknowledgement? Yes. So as I said that there are uplinks, right? When we are sending just uplink, we do not wait for an acknowledgement. But there's something called confirmed uplinks that you could always transmit. And the gateway or the network server has to give an acknowledgement back. If you're using a class AN device, that acknowledgement should come within RX1 or RX2 window. So you could use a confirm uplink or a confirm downlink if you want to have an acknowledgement in the LoRaWAN protocol. So yes, it does serve that purpose. Is there any duty cycle limitation in India? It's a very good question. In India, we don't have it as of yet. So that's not what's there in India. Can you explain the duty cycle limitation in LoRa? Yeah. I think I would want to explain that in detail, what's duty cycle and what are the limitations and why we do that. So I would love to answer that question in details, and Mukarram for sure via the email, what basically duty cycle means, because probably that why we do that. If we want to know that, it's basically to not have, so it's basically to have a better running network, because if all the devices are sending and they are not waiting for the others to send, basically we hurdle our network, we have a lot of interference. In case of LoRaWAN, we have duty cycle limitation in all other countries. What that means is that after uplink transmission, you have to wait for a certain period of time, right? That is defined by the duty cycle. In that time, we basically allow the other end devices to communicate. That essentially prevents the network to be not getting overburdened. So that's duty cycle. But I will take that as a agenda in the next webinar 201, or I would just give you a detailed discussion, or we could call for sure to have a long discussion on that. Perfect. Thank you for your, okay. Can we control end device with controller that is central management? Yes. So LoRaWAN essentially gives you the ability to send downlinks, right? So at the central management, if you are referring it to the network server, you can send the MAC clear instructions to the LoRaWAN. From the application server also, if you want to do some instruction, you could just do that, because we at LoRaWAN supports downlink communication as well. So yeah, you could do that. You could control your end device. In fact, you could do firmware over there updates. That's also possible in LoRaWAN. If you want to change the firmware, you could do that using LoRaWAN. That's the thing. Okay, so there's another question that how LoRa technology works for logistics industry, as LoRa needs LoRa gateway to communicate, and LoRa gateway has certain limitations. I would wish if that question was a little elaborated, the limitations I was trying to understand. But answer to that I would give is that, yeah, so in a logistic industry, if you are talking about an indoor environment, we also have LoRaWAN indoor gateways. But the limitations, I would want to know what that means. Each gateway, if you're talking about Pico gateway or micro or macro gateway, has its own limitation, right? The capacity of that gateway and so on and so forth. So yes, gateways have certain limitations, but if you'd want to understand how the LoRaWAN works in logistics industry, you would want to check the just previous webinar that we did. It will give you almost all the answers. If you still are not getting all that you want, we are there. I'll just drop you an email and we can discuss in detail. Cool. Okay, so another question is that why go for LoRa instead of LPWAN? So LoRa itself basically is part of the LPWAN technologies. There are multiple other LPWAN technology like weightless P, weightless N, Sigfox and all of that. Each of them has their own advantage. But if I were to say, why would I go for LoRa? For example, in case of weightless P or N, I don't think that there is a downlink compatibility. You have to go back to the end device if you want to change something. But LoRaWAN does give you the capability to the downlink communication. And it basically has impressively low receiver sensitivity compared to all LPWAN networks. So that's why go for LoRa. But it's not instead of LP1 because it's also a part of LP1. So yeah. Cool. So I trying to understand this question. How can we reduce the time cycle between sensors and relays, as the time cycle is usually between 2 to 6 seconds as per our experience? Okay, so I believe that you're trying to say that when you want to have your relays and sensors working in time, there's a delay of 2 to 6 seconds, as I can understand from your question. If you probably want to mitigate that, then note that we could always use a higher data rate. And that is something that would allow you to remove that delay. Right? So yeah, a higher data rate option would do the best for you if you want to have a lesser delay. If you don't want an even lesser delay than 2 to 6 seconds. Okay. Cool. Okay, so carry on, change your question instead of other LPWAN. So as I told you, we have downlink compatibility in LoRaWAN. So that's something that I would say the other weightless PR doesn't have. We can have a very healthy discussion on that. Why would we choose the other? Because there are a lot of factors. We have cost. Do we even have the other LPWANs across the globe, which has the maximum community strength? All of that also matters when we are trying to decide which one you would want to go for. As you see that SenRa, we basically have already covered almost all the cities in India, the smart cities in India. We have already covered 73, 74 smart cities. So we already have an infrastructure there. So everybody would want to go for something that's omnipresent, right? So that something is also a factor. There are other factors that are involved. There are costs and everything. We could have a complete discussion on that. I really love that question. Cool. Let me see if I've missed. So I see a lot of questions, guys. I have a hard time taking each one of them. I'm sorry about that, but I have seen that all the questions are really good. If you really want to get deeper into everything, for sure, the LoRaWAN 201 and 301 would be great for you. Because as I see, there are a lot of questions that you have been asking about the code rates and what's the total size and all of that. That has to be covered. That has to be covered in a separate section. That was only meant to be given to the newbies. So yeah, let me see if I can answer another 2 questions in the time frame that we have. Okay. So is there an encryption policy at LoRa node during communication with gateway? Yeah, so that's a good question. For that, I would request you to go for the patents, but I'll just give you a very basic understanding that the file layer in almost all communication technology also provides some security mechanism. And in LoRa, basically, it is given by when we have a payload, that payload has to go for a gray indexing, and it goes to a whitening sequence. And that whitening sequence is essentially zoring your bits to a pseudo-random sequence. And if that pseudo-random sequence is known to both transmitter and receiver, then only basically we can make sense out of what is going on. So that's something, a very basic encryption policy at the LoRa itself. But in case of LoRaWAN, encryption and the security mechanism is even sophisticated. We have network session key, application session key, within which we encrypt our data, and those session keys are known to both gateway and the end device. So if you're using LoRaWAN, you're more secure for sure, but the FireAir itself also gives a functionality of encryption policy. Cool. Perfect. Let me see if I have anything more. So yeah, guys, you can reach out to us using info@senraco.com, right? That's something that where you could reach us out at. I'll just again share my screen to you just so that you know that this is where you want to reach out. I would love to answer all of the questions, because since we are limited in time, I cannot do that. I'm really sorry about that, but the questions are really interesting, and each one of them should be given a separate time for a discussion. And this is the place where you would want to go for all the discussions that you would want to have. We have info@senraco.com. I would take up all these questions one by one and would give you a detailed answer of each. You could visit our LinkedIn website. That's where we post all the details, things about the next webinars that we are going to have. senraco.com is the website that we have. Yeah, so this is where you could reach us out at. There are a couple of questions that are left, and I would be back with the detailed answer to those questions just so that you're very much convinced over everything. Cool. See you guys in the next webinar. I'm really excited about it. We have already started working on it, and I'll be back with a more detailed form. Thank you all very much.